Oh, yes. So this is at sigma equal to minus L to sigma equal to plus L. Okay. And because this x mu has the same value at sigma equals to 0 or sigma equals to minus L if you like, as you like, and sigma equals to plus L. So let me not change it with that. This is sigma equal to 0, sigma, what did I write here? Sigma plus L. Okay, so it's periodic, sigma equal to 0, sigma equal to 2 pi. So this has the same value at sigma equal to plus L as well as at sigma equal to minus L. So it is minus T d tau, some value minus the same value, and it is 0. This is another way of understanding it. And the third one, which is due to my friend Christian Knoll, which appealed to me very much. It's little more, it sounds to me a little more mathematically rigorous. You see, the boundary of any object has one dimension less than the object. So for volume, you have the surface. For surface, you have a curve, and for the curve, there would be no boundary. This is another way, or if you put it, or if you put it like that. So omega, and you further go to the boundary of this boundary, and so it's a closed curve, and closed curve is a one-dimensional object, and you then take its boundary, it gives you 0 again. This is also, to me, it appeals very much, okay? But nevertheless, all the three, they imply that this boundary term should vanish for the closed string. Well, this is the simplest case among the closed and open strings, but in open strings, it's little more tricky. So we can remove this, and we again come back to these boundary terms, and now we let me, you see, this is a product of two things, x prime and delta x. And we have to somehow choose. We are now talking with respect to the open strings. So at any end, where we apply the boundary condition, we have to deal with a product of these two terms. So simple thing that comes to mind is either this should be 0 or this should be 0. Okay. And so we define our boundary conditions in such a manner because we know in our mind that the boundary terms have to vanish, or we want to make them vanish. Okay. So it's a matter of how do we choose our boundary conditions. So you here, or it's not necessary, it can be here, it can be here. Now here is, if I in the reaching a boundary condition, I want to keep it fixed. I want to keep the end of the string fixed. I do not want to allow it to fluctuate or move, which means I fix it at some value, and I also fix it at some value. The two values need not be the same, they can be different. So just a simple illustration, one here, one there. So the x mu is fixed here, which means delta x is 0. X is fixed here, so delta x is 0. So I have applied Dirichlet boundary conditions at both the ends. And as a result of that, what happens that this guy becomes 0. Delta x becomes 0 because x is fixed. So delta x variation is 0. That would be Dirichlet boundary condition. What happens to Neumann boundary condition? This could be somewhere, this, and now let me make it dotted here or any say. So here x is not fixed. Here also x is not fixed. So delta x is not 0. Also here delta x is not 0. But I want to make my boundary terms vanish. What do I do? So I propose that okay, let delta x mu be non-zero, but let x prime mu be 0. So I allow the end of the open string to fluctuate with the additional imposition that its space derivative vanishes, so that the product of these two vanishes. Here I say x mu at 0 is a constant, x mu at L or 2 pi is also a constant, which is different than this, and therefore the delta x0 mu is 0, delta x mu 2 pi is also 0. This is Dirichlet boundary condition. I can also have a mixture of these two. I can keep only one end fixed. I fix it. So x mu 0 equal to constant, then delta x mu 0 is 0. That means this is Dirichlet boundary condition. So this does not fluctuate. It is fixed, pegged at one point, nailed at one point. Okay. Whereas, so here delta x, no, x mu is not constant. Is not constant. So delta x mu is not 0. However, x prime mu is 0. So whenever I have the Neumann boundary condition, I must have x prime equal to 0. So we can have a mixture of the two. At two ends, I can have Neumann, Dirichlet, or Dirichlet Neumann, or Neumann Dirichlet. It's my choice, and accordingly. But in all the cases, these sigma boundary terms also must vanish. But here they were little more non-trivial than the tau boundary conditions. For the time tau boundary conditions, there was a term delta x mu, which was going to 0 at tau equal to plus infinity as well as at minus infinity. So they did not help us classify our different kinds of strings. What kind of string we have, closed or open, and open then which kind of boundary condition. But for sigma terms, it leads us to a very consistent way of classification of these boundary conditions. And this really leads us to the proper string theory, right? So with this, one can then proceed. Because they are so important, I might take another 5 minutes or so to just see what happens to the Poincare invariance of these terms. So I think I could remove this and so for the Dirichlet boundary conditions, we look at the Poincare invariance of the terms. So my x mu goes to x tilde mu equal to a mu x mu plus b mu, and this I consider at sigma equal to 0 and at sigma equal to pi. So this also I consider at sigma equal to 0 and sigma equals to pi. So what I have is, this is a mu nu, this would be x nu 0 or pi plus b mu at 0 or pi, and you see x nu for Dirichlet boundary condition from that figure as well as